Today we are going over improper integrals, and the basic terminology we would want to know is that divergent means it doesn't exist, and convergent means it can exist. This is normally determined by the outcome of our answer on whether it's infinity or negative infinity, which it doesn't exist, so that would be divergent. And the way I would like to remember that is that there's a D in divergent for doesn't, and then any finite real number, such as for example 5, is convergent, which can exist, which you can determine by the C in convergent. And so that's how I like to remember them. Now, there are a few types of improper integrals that I want to go over, which are infinite limits of integration. So for example, in our integrand, our bounds can be from A to infinity, or it could go from infinity to B. So this is the example given. And then there's also a discontinuous integrand where it goes from A to B, but for example, we're given a fraction 1 over x minus 3. So 3 cannot be an answer in that case because you can't have a denominator of 0, which doesn't exist. So you're going to have to change up your bounds. And in this case, we would have to change it from 0 to 3, as well as 3 to 5, which as you can see, I just replaced the B bound over here, and then I just replaced the A bound over here for this integrand. I just split it up into 2, but I will get more specific into how that works in the video. So let's begin our first problem. So our first problem is going to be the integral of x over x squared plus 1 squared bounded from 0 to infinity. Now the first thing you want to do is write this improper integral into a limit. So all you do is just replace this infinity sign with any variable, and I'll choose t, and we can set our limit to approach the infinity instead. And then the inside of the integral stays the same, which we can just further evaluate using u substitution, making our u x squared plus 1, so we can cancel out the x on the numerator, making our derivative 2x dx, and then making our dx equal to du over 2x. And assuming y'all know how to do u substitution, we'll take out the 1/2 and set it to 1 over u squared, which will then integrate to negative 1 over 2u plus c. And then we can substitute back our u. We can then set up the definite form of this integral, but let's first put our limit outside of it and then put our result inside a box, and then bound it from 0 to t. We then get limit t approaching infinity, negative 1 over 2 t squared plus 1 minus negative 1 over 2 times 0 plus 1. We can then just simplify it to the limit t approaches infinity times negative 1 over 2 t squared plus 1 plus 1/2, because a negative and a negative make a plus. And how I like to look at this limit is t equals infinity. So when we set t equal to infinity, which is basically 0 at that point. So then this just ends up becoming positive 1/2. And you could add the 0 in front if it helps, but overall, the answer is 1/2. Now, based on our definitions over here, would this be considered convergent or divergent? Now, since this is neither a negative infinity nor an infinity, and this is in fact a finite real number, this will be considered convergent. So our final answer will be 1/2, convergent. And we just solved our first improper integral. I would now like you to do this second problem on your own. So this may look like a simple u substitution problem, but it isn't. And the reason is because of this 0. If we were to set our sine of x to 0, our denominator would have a 0, and a cosine divided by 0 does not exist. So therefore, this is actually an improper integral. So in comparison to our first problem, we had an infinity sign in our integrand, making it fairly obvious that it was improper, but over here it's improper because of the dividing by 0. So let's just take our limit as t approaches 0 from the right. And determining approaching from the left or the right just depends on the other bound, and since we are approaching towards this pi over 2, it is going towards a positive area. So from 0 to pi over 2, you would use positive numbers to get to pi over 2. So we can write the integrand as cosine of x over sine squared x dx, sorry, that's a train, from t to pi over 2. So for now, we could just ignore this limit, but we will get back to it. So let's just evaluate the integral itself, which again, assuming you know how to do a u substitution, I will just skip all the steps to end up getting negative 1 over sine of x plus c. We can then go back to this limit as t approaches 0 from the right and put in brackets our 1 over sine of x from t to pi over 2, which simply gets us negative 1 over sine times pi over 2 minus negative 1 over sine t, which again all goes in coordination with this limit of t approaching 0 from the right, and our box just simplifies to negative 1 plus 1 over sine of t, again under our limit, which then plugging this t for infinity just gets us -1 plus infinity, which of course is infinity. So because our answer is infinity, would this converge or diverge? Well, looking back at our definition, negative infinity or infinity does not exist, and because it does not exist, which starts with the letter D, doesn't, it will be divergent. And again, if it can exist, it would be convergent due to it starting with C. So our final answer is infinity divergent. Our third and last problem is going to be the integral of 1 over x minus 2 bounded from 1 to 3 dx. Now in our denominator, our x cannot equal 2, so it is discontinuous at 2. But in our bounds, 2 is not shown. But then you begin to realize 2 is in between those bounds, so what you can do is just split it up by putting the bound from 1 to 2 and adding it to an integral whose bound is from 2 to 3. And if you notice, it's still bounding from 1 to 3. All we did was split it up and the 2 is in between. So I guess if you're having a hard time seeing how that works, you could just put it like this and notice that it's going from 1 to 2 and then 2 to 3. But anyways, let's just see how that looks when we actually put it in integral form. And there we go, we split the integral. Now you're going to want to set a limit for each one, where for the first half of the split integral, our limit can be t approaching 2 from the left, because we're going from 1 to 2, which is from left to right, and we can have our other half of the integral go from limit of t to 2 from the right, because it's going from 2 to 3, which is going from 2 to the right, because it's going up by 1. So here, our 2 was going down to 1, and then here, our 2 is going up by 1, if that's how you want to remember it. So now we can substitute the 2 on each one for t, which in turn just gets you this. And from here, you would just do a basic u substitution to actually find the integral, which is the natural logarithm of the absolute value of x minus 2, and then bound it from 1 to t, which is testing this first half of the integral. And don't forget our limit, which then equals the limit of t approaching 2 from the left, natural logarithm t minus 2 minus the natural logarithm of the absolute value of 1 minus 2. And once you plug in our 2 over here into t from our limit, you end up getting negative infinity as a whole. Now, this saves us a lot of time if we find out that one of them doesn't exist, which clearly one half of the integral doesn't exist, it's the first half. And if you solve the second half, it also won't exist. But since one part doesn't exist, this overall will diverge. You don't have to test both, you can only just test one if one of them diverge. Now, if one of them converge, make sure that you test the other one just to make sure it doesn't diverge. But yeah, that is our lesson on improper integrals. Thank you for watching.